Good afternoon, good morning, good evening, our global audience. Welcome to the Sparse course series on fundamentals of a channel knowledge map from classical to AI-based methods. So this course is organized by Sparse, which is an open platform dedicated to fostering academic exchange by connecting researchers, scholars, and professionals across various cutting-edge disciplines. So my name is Xu Jie. I'm from the Chinese University of Hong Kong at Shenzhen. So today we are delighted to have Professor Yong Zeng. He will give us the lecture on CKM construction by using generative AI methods. So before we start, let me have a brief introduction about Professor Zeng. Professor Yong Zeng is actually a fellow. He's a young professor with National Mobile Communication Research Laboratory, Southeast University, China, and also with the Purple Mountain Laboratory, Nanjing. He received a bachelor and a PhD degree from Nanyang Technology University, Singapore, and then worked as a research fellow, senior research fellow, and a lecturer at the National University of Singapore and the University of Sydney. Professor Zeng is listed as a highly cited researcher by Caribou Analytics for 7 years. He is a recipient of Australian Research Council or ARC DECRA, and also he received the 2 IEEE Marconi Paper Award in Wireless Communications and the IEEE Communication Society Asia Pacific Outstanding Young Researcher Award and many other awards. Professor Zeng proposed the concept of a channel knowledge map. He has published more than 200 papers, which has been cited by more than 35,000 times. He served as an editor for IEEE transcriptions on communication, mobile computing, communication letters, and many other journals. And he was elevated as an IEEE Fellow for contributions to UAV communications and wireless power transfer. Without further ado, let's welcome Professor Zeng to give us the lecture. Okay, so Yong, the screen is yours.
Okay, thank you, Professor Xu.
You may share your screen.
Yes. Yeah, can you see my screen now?
Yeah, it's quite clear.
Okay. Oh, hello, everyone. Thanks again for joining us today. Today, we are going to discuss CKM construction by using AI, and in particular, generative AI. Okay, let me first full screen. So in the first lecture, I gave some background about channel knowledge map. So why we need to propose the concept of CKM and what is the definition of CKM. And we also give some typical usage examples for CKM for communication, sensing, and localization. And I also give some CKM construction problems. And last week, Professor Chen gave a course on how to construct a CKM by using some interpolation and supervised learning methods. So today, we are going to further discuss the CKM construction problem. So I will first recap the CKM construction problems. And I will show that image processing is very useful for CKM construction. And then for the so-called transferable CKM construction problems, we will first show how to use a supervised learning approach. And then we believe that generative AI is a very promising technology to construct a CKM. So first, what is CKM? We define the CKM as a mapping from the transmitter-receiver location, Q, to the channel knowledge vector, Z. So let's say in a wireless environment at location QT and QR for the base station and the UE, then these two locations actually have rich information about the environment. So in this case, if we can learn from the environment, we can actually build a mapping from the location vector Q to the channel knowledge vector Z or its distribution conditional on this location vector. So if we want to construct a CKM for all possible areas, then the first step we need to do is to collect data that contains the location-specific channel knowledge. So for the data M, we have the location vector Qm and the channel knowledge vector Zn. So this channel knowledge vector can be any channel state information. It can be the channel gain, delay, angle of arrival, and so on and so forth. So actually, we have different methods to collect the data. It can be offline, it can be online. It can also based on some computation, let's say the ray tracing based on certain physical environmental map, or it can based on some historical data from our communication devices, let's say the mobile terminals. We can also deploy some dedicated measurement devices to collect the data for channel knowledge map construction. So regardless of the actual methods we use to collect the data, we have the location-specific channel knowledge QM and ZM. But we cannot have the collection or the measurement for all continuous locations. So a very basic CKM construction problem is that, let's say we have collected a data set for the area Q, and we can also specify certain environmental information about this area Q. But because we cannot connect the data for all locations, then we need to do something to find the CKM for all possible locations in this area. So if the data connection area Q and the CKM construction area is the same area, let's say for this base station coverage area, we have collected a set of data, and we also try to construct the CKM for this base station. Then we call this as a non-transferable CKM construction because both the data collection and the CKM construction share the same area. So actually, we discussed some methods, and also Professor Chen discussed the methods to do CKM construction for this scenario. So let's say we can select certain model, or if we just use a data-driven approach, we do not need to select any mathematical model. We just train a neural network for this kind of CKM construction. So typical methods include, let's say, the interpolation-based methods. So we can have the so-called IDW, inverse distance weighting method. We may have the nearest neighbor method. We may also have the KNN, Kriging, and so on and so forth. And we also mentioned that we can train a neural network to find the mapping from the location vector Q to the channel knowledge vector Z hat. We may also combine the data and also the mathematical model of wireless environment or wireless channel. For example, if we want to construct the channel gain map for a base station, then we know that we have a very well-established mathematical model, let's say the path loss model for the channel gain. For a location vector Q and a base station vector QT, then the distance can be obtained, and based on this distance, we can find the path loss model. But if we just use the single set of parameters, we will end up with a path loss model or channel gain model that is isotropic in all directions. It means that it only depends on the distance. But of course, we can use more complicated mathematical models. Let's say we can use a multiple set of modeling parameters. We can partition the area, so let's say depending on the actual environment, the buildings and the building properties. We can, let's say here, we can partition the environment into 5 subregions. For each subregion, we can find a mathematical model with different parameters to estimate the path loss or the channel gain. But let's say if we only have some random data sample with sparse measurement, or we can also have some grid sampled data. Let's say for every d meters, we have one sample data. Based on this sampled data, we try to construct a complete CKM for all the possible locations. So based on the mathematical model we discussed just now, for those locations without any measurement, the correlation between the channel gain, in particular, the correlation between the shadow invariance between the different locations is a mathematical foundation for us to actually predict the channel gain without any measurement. More specifically, let's say if our channel gain is decomposed for the path loss, and this one is the shadowing, and here we also have the small scale fading. For small scale fading, we cannot do anything because the channel coherence distance is very small on the wavelength scale. But for shadowing, we know that for a location at Qi and another location at Qj, we use, let's say, as an exponential function of the distance h. Because of this correlation, we can make use of the measurement result on the neighboring locations to actually estimate all possible locations within this area. So the steps are very simple. We first, based on the location, to find the path loss, and then we estimate the shadow invariance, or estimate the shadow fading at this location Q, let's say based on the k nearest neighbor measurements. And then we treat the small scale fading as noise because there's nothing much we can do. Then a fundamental question is that for this kind of setup, how much data do we need for this channel knowledge map construction? It basically means that, let's say for random data sampling, what is the sampling density lambda? Or for this grid sampled data, what is the grid size? Let's say for every 1 meter or 10 meters, we should sample data in order to achieve certain performance metrics for CKM construction. So in this TWC paper published in 2024, we try to answer this question: how much data is needed for CKM construction based on this method? So we know that if we do not have any data, the variance of shadowing based on this model is alpha, and we may also have a variance modeling for the small scale fading, let's say sigma square. If without any measurement, then our variance or uncertainty for any channel gain is just the variance of the small scale fading sigma square plus the variance of the shadowing fading alpha. But because we have additional measurement at the neighboring point, then the variance can be reduced if we use the measurement from the neighboring locations to actually predict the location of Q. So in this case, we can have a reduction of the variance. This is because of the spatial correlation. But this is just for one particular location Q. For the network perspective, we want to find the average MMSE after taking the average for all possible locations within the base station coverage. So in this paper, we have derived the mathematical closed form expression of the mean square error for the channel gain prediction as a function of the signal, the data density lambda, and also as a function of how many neighboring points or neighboring locations we use to predict the unmeasured location. So this is K. So for both the random sampling and the grid sampling, we have a closed form result. So we found that, let's say, if we want to achieve certain average MMSE, let's say for 6 dB square, then we know what is the density lambda to sample the data. So this is actually a very theoretical work to show how we can make use of the spatial correlation of the channel gain, as well as the data to construct a CKM, here is a channel gain map, so that we can achieve certain expected performance in terms of the MMSE. But this mathematical analysis is quite restricted to this channel gain map construction. For other channel knowledge, let's say the angle of arrival, the delay, it is very difficult to find a similar result. So here we can summarize the limitations of the interpolation-based channel knowledge map construction. The first limitation is that the mathematical model we have developed over the past few decades actually do not fit the complex environment. For example, in the city, in the urban environment, actually the personal modeling is much more complicated. The second limitation is that the mathematical model actually is very hard to extend to other channel knowledge. For example, for the angle of arrival, angle of departure, or delay, although we also have similar mathematical models, the analysis is much more difficult. And the other limitation is that for interpolation-based method, either it is a KNN or the spatial correlation-based method, we actually only use the local data to predict the channel knowledge. Let's say for the KNN, K nearest neighbor, we only use the K nearest neighbor data to predict my current channel knowledge, but the data collected in other area or in other city is not used. Actually, the fourth limitation is that let's say we have collected a large amount of data in other area, let's say in Beijing or in Nanjing, but we want to construct the CKM for another city. So how to make use of the data connected in all other areas to construct a CKM? This is the CKM construction problem we mentioned last time, which is called a transferable CKM construction. But for the techniques we discussed so far, it is very difficult to make use of the data connected in other areas to transfer the knowledge or the data information learned in one area to another area. So this will be the focus of today's talk. So let's first recap the CKM construction problem for transferred knowledge. So let's say here we have a very similar CKM construction problem as we discussed just now. The difference is that now the data set or the data collection can be from one area, let's say Q1, but we want to construct the CKM for another area. So how to make this make use of the data connected in one area to another area? Of course, we may also give some specifications for the environment Q2 for which we want to construct the CKM. So we call this as the transferable CKM construction. The key questions are, is the data collected in area Q1 useful to construct a CKM for another area Q2? So this is one of the questions we raised last time. And how to specify the environmental information for the area where we need to construct a CKM, and how to transfer the knowledge learned from one area to another area. So in order to transfer the knowledge learned in one area to another area, intuitively, the key idea is that we should eliminate the dependence on the absolute locations. Remember that for the data set we mentioned, we have the raw data set. The raw data set includes the transceiver location QM and the channel knowledge. In order to transfer the knowledge from one area to another area, we should somehow eliminate this dependence on the absolute location QM. Instead, we should consider the so-called relative locations or relative displacement. So the basic idea is that instead of considering just one single data point, we should consider M data points or M data locations jointly. So for example, if we want to construct a CKM for this area with a base station coverage, we can actually partition the area into small regions or small patches. Each has a pixel or locations, number of locations H times W, where H and W is the height and the width of the patch. And if we fix the relative locations for all the pixels within this patch, we actually can construct a large number of data that is independent of the absolute location Qm, but only depends on the relative locations or relative displacement data 1 and data m. For example, for every 1 meter, we sample one data point, one location. Then let's say if we construct 128 pixels or locations horizontally and also vertically, we can construct a data set that includes 100 times 128 times 128 data points together. And let's say in this case, our channel knowledge Zn has a dimension j prime. Then our data, processed data, will have a dimension h by w, where h by w is the total number of location pixels or location grids that we need to consider jointly. And j prime is the dimension of our channel knowledge. And we can put all such data into one single data set. In this case, we no longer have the absolute location Qm. In this case, the beauty is that we can collect all such data sets into a huge data set. It is no matter whether it is from Beijing or from Nanjing, as long as we have processed the data within this standard, it will be very useful. But the key challenge is that let's say we consider m is 128 times 128. The dimension of the data will be huge, will be more than 16,000 locations for each data point. And for each location, the dimension j prime, it can include the gain, angle of arrival, angle of departure, and delay. It can be 7 or even larger than 7. So this actually convert our raw data in terms of the location and channel knowledge to the kind of image style. So the height and the width of the image depends on how many data points or data locations we consider jointly. And the number of channels for the image depends on how many channel knowledge. Let's say whether we only consider the channel gain, or we also need to consider the angle of arrival, angle of departure, and delay, and so on and so forth. So in this case, we have actually constructed a data set kind of very similar to the ImageNet data set. So in this paper, we call it a CKM-enabled data set. The key idea is that we try to remove the data dependence for the absolute location, but it only depends on the relative locations. So by this way, we can actually reformulate the CKM construction problem. Remember that for CKM construction problem, we were given a data set, but now in this case, the data set is no longer given in terms of the absolute locations. It is given in terms of the image-like X with dimension h by w and by j prime, depends on how many locations we consider jointly. And of course, we also need to give some specification for the environment where we need to construct the CKM. And you can find the CKM now also in terms of the image X. So let's say we want to construct the CKM for this area Q2. Again, we can represent the CKM in terms of the patches. For every h by w locations, we consider a CKM jointly with image-like representation X. So in this case, we can construct the complete CKM for this area. So now the problem will become, we have a data set X. It can be collected anywhere on the Earth, as long as it follows certain standard. And we specify the environmental information for this Q2, and we try to construct the CKM, which is represented by a tensor, by a high dimensional tensor. But the next question is that how can we make use of both the data set and also the environmental information to jointly construct a CKM? So remember that we have two inputs. One input is a data set we have collected maybe from anywhere. The other input is the environmental information for the area Q2, where we need to construct the CKM. There are actually different scenarios. The first case is that, let's say we do not have any environmental information for this Q2. The second case is that we have full environmental information. Let's say we know the buildings, we know every details of the building, the materials, the building height, and so on and so forth. And the third case, and also the most important case, is that we know some partial environmental information. So let's first consider the second case. If we know the full environmental information, actually, we can use some, let's say, traditional computation or ray tracing method to calculate the channel knowledge map for this environment, for this area Q2, because the environmental information is sufficient for us to do the ray tracing. Then maybe the data set contained in X is unnecessary. But if we only know the data set without any environmental information, of course, we can still learn some distribution or some knowledge from the data set. And we may sample a CKM based on this data set, but there's no guarantee that the obtained CKM will match with the ground truth CKM for the area we want to construct. This is actually quite easy to understand, because without any specifying any environmental information for the CKM for the area we need to construct a CKM, there's no way that we can construct a CKM that match exactly with the ground truth. But for the third case, if the environmental information is insufficient to perform the CKM computation, and then we can learn some pattern or some distribution of the CKM from the data set. And based on this tool, we can actually construct a so-called guided CKM construction, so that the obtained CKM is consistent with the environmental Q2, and also it follows certain probability distribution of certain feature for the CKM. So this is actually the most important case where we need to study. So the tool input, the data set, as well as the environmental specification will be both important for us to construct a CKM for the area Q2. But now the next question is how to actually specify the environmental information. We know how to model the data set in terms of the image X, but how to specify the environmental information? Actually, there are many different ways. The first possibility is that we can specify the physical map. Let's say it can be a 2D map or a 3D map, but the map may not be sufficient for us to construct the CKM, because let's say we do not know the material, we do not know the so on and so forth. The second possibility is that let's say we have obtained the point cloud of the environment. We may also, based on the photo taken from a camera, this will actually contain much rich information for the environment where we need to construct a CKM. We may also specify the environment based on the radar output. Let's say this is the radar, the range and the angle, the radar output. Then this also contains some information about the environment. Of course, we may also describe the environment by words, by language. Let's say here, please construct a CKM for a downtown area with the average building height of 20 meters. We may also specify the material and so on and so forth. This, of course, also includes rich information for a wireless channel. The last possibility is that we may also have some sparse channel knowledge observation for the area where we need to construct the complete CKM. So actually, this is the simplest case. And today, we will focus on the last case. And the remaining case, the so-called multi-model environmental specification, together with the data set to construct a CKM, will be discussed in future works. So let's say consider the sixth case, the sparse channel knowledge observation. What does this mean? In this case, our CKM construction problem will look like this. Again, we have a data set. It can be from anywhere. And we specify the environment for the area we need to construct the CKM based on some sparse observations or some degraded observation Y. Let's say it can be sparse or noisy observation. And we want to find the complete CKM X for this area Q2. So here, let's say we have an observation Y where certain part is missing because we do not have the complete observation. But fortunately, we have the data set so that it can provide additional information so that we can construct the CKM for this area Q2. This is the basic problem setup for the so-called CKM construction with sparse observation. So we can actually formulate the problem like this. We have an observation Y. It can be a sparse or some noisy observation. We have a ground truth CKM X, which is a high-dimensional tensor with m locations. And each location has a channel knowledge of dimension. Let's say J prime is 1 for channel gain, or it is 7 if we want to construct the channel knowledge for both channel gain and the delay and the angle of arrival. So X is something we need to reconstruct or we want to estimate, but we only have some partial observation of Y. Based on this Y, we want to infer X. This is actually a very classic so-called inverse problem. It includes actually a large number of possibilities. For example, the first possibility is this is the ground truth X, the channel knowledge map we want to reconstruct. Let's say this is 128 pixels in both the horizontal and the vertical domains. But because in certain area, we cannot have the measurement. Let's say this box, will have no measurement data. Okay, then in this case, the forward operation A is just a masking operator with it can be a linear with ones and zeros. The masked region will have no observation. But we want to solve the inverse problem. Basically, we only observe the Y, how to reconstruct X. So this is a classical image imprinting problem. The other possibility is that, let's say because of the high cost for measurement, we do not have the complete measurement for all the possible locations X, but we have very sparse measurement. Let's say for every 10 meters or even 20 meters, we have one measurement. And then the observation Y needs to be used to reconstruct the ground truth X, which is a super resolution problem. We may also have this quantization operation because of the limitation of the measurement device. We may have some quantization error. So we only observe the quantized CKM, how to do the quantization recovery. We may also have the truncation error. The ground truth channel knowledge map X is truncated, and we only observe the truncated CKM Y, how to reconstruct the complete CKM X. So in this case, we have different scenarios for the CKM construction, but they can all be modeled as a inverse problem. So for example, this is an incomplete CKM. We can do the CKM imprinting, and the low resolution CKM, we need to do the CKM super resolution. Of course, if we only make use of the observation Y, we do not do much about the recovery. But remember that we still have the data set. Here we use the so-called CKM ImageNet data set we discussed just now. And this data set contains rich information for us to reconstruct the CKM even with degraded observations. And even the observation is noisy. A very classical problem is to do the noise removal. And this is usually the case if our measurement device has noise. So let's try to understand this problem. We have formulated the problem as an image processing problem, but our image is somehow different from the natural image. Here, H and W, of course, we can choose our H and W based on our data set. And for typical image, the number of channels, 3, actually is just at most 3. For a colored image, the number of channels is 3 for RGB. But for our CKM, the number of channels can be huge because it really depends on what need to be included for CKM. For the CKM we discussed last time, if we want to include all the possible information, let's say the channel gain, the path gain, the angle of arrival, angle of departure, and delay of each path, the number of channels can be huge, especially if we want to do some probabilistic based CKM, then the number of channels will be much greater than 3. This actually is quite challenging, which is different from the image processing for the natural image. So that's why most of the existing work mainly consider the so-called radio map or channel gain map reconstruction. So let's try to understand the big picture. Remember that we have a CKM construction problem as the inverse problem. This is very similar to the image processing problem. Let's say we have an observation of the dog with certain part masked, and we want to reconstruct the complete dog. And fortunately, we have a data set of dogs. So this data set will tell us a dog should look like something we can visualize a dog. This is very similar to the CKM construction. If we do not have this data set, this actually based on the observation Y, there's no way that you can reconstruct the CKM X hat with high fidelity. But again, we know based on the data set, we can learn the pattern of the CKM. The CKM pattern or the CKM image should look something like what. So this is very similar to an image processing problem. But the key point is that how to do the pattern learning. And actually this is just the standard generative AI method. Before we discuss the generative AI, let's try to consider a very simple, very standard manner to solve the so-called inverse problem. Remember that either it is a CKM impending, CKM super resolution denoising, we can formulate the problem like this, a linear inverse problem. So we want to estimate X based on the observation Y. And a very straightforward manner is that we can make use of the data set. Let's say if we have a data set that with the paired data X and Y, then the input is Y and we want the output X. Very simple. We just train a neural network. Let's say a deep neural network, a feed-forward neural network with input Y and output X. And we can optimize the network parameters so that the estimated X and the ground truth X, the error, let's say the MSE, will be minimized. This is a standard supervised learning approach. Then by this approach, we can construct the CKM X. So here we use this method to do the CKM super resolution. So let's say we have a sparse channel knowledge data, let's say the channel gain, and we want to reconstruct the complete CKM. Then what we can do is that very similar to the image super resolution, we can train a neural network like this. The input is the data set XM, and we can do the downsampling to obtain the degraded CKM YM, and this is the input, and then we train a neural network. And during the inference stage, we only need to input the sparse data Y so that we can predict the complete CKM X. And by this way, we actually can achieve a much better performance as compared to the traditional interpolation-based methods. The main reason is that the conventional interpolation-based method does not make use of the data set we collected from other locations, right? So here we can compare the performance, the proposed super resolution-based method with deep neural network as compared to the conventional interpolation-based method. Also for the GAN-based method, we can find that the the RMSE can be significantly reduced, and the PSNR peak signal to noise ratio and SSIM can be improved. So this is one example to use supervised learning method to construct the transferable CKM construction. So this supervised learning method is different from the supervised learning method discussed by Professor Chen last week, because here we can construct a CKM that is so-called transferable. But the limitation for such supervised learning method is that here the first limitation is it is very difficult to generalize. What does this mean? It means that, let's say, a model trained for task A, let's say for super resolution, cannot be directly used for task B, let's say for imprinting, because they have different input-output relationships, so that the network we trained for one task cannot be directly used for another task. This is one limitation. Let's say if we have super resolution, imprinting, denoising, and different tasks, it means that for each task, we need to train one deep neural network. This is not effective. The other limitation is that such supervised learning method always requires the labeled data or paired data in terms of k, y, and x. So y is our input and x is our output, or the label. Another limitation is such kind of method has the issue of so-called regression to the mean. What does this mean? This is because for any observation y, we have many different possibilities for x that lead to the same y. So it means that if we want to estimate x based on the observation y, there are so many different possibilities. Then the supervised learning method usually tries to give the so-called conditional mean. It gives the average of all the possibilities. So this will give us the blurred image that cannot capture the details, and it has a poor perception quality. So these actually are the limitations for the supervised learning method for CKM construction. So in order to solve these issues, we can use the state-of-the-art AI method called generative AI. So what is generative AI? Remember that, again, we consider this inverse problem. This is a ear-post inverse problem because, as we mentioned just now, the observation y is a degraded observation. Let's say it is a sparse observation. Many CKM x may lead to the same observation y. So if we only base on the observation y, there's uncertainty or ambiguity for x. But remember that for this kind of inverse problem, we have some method, let's say the maximum a posterior probability estimation, where if we know the prior distribution of x, then we can actually narrow the possibility of x. So this will actually give us a more effective method to do this estimation. But the problem is that we try to learn the prior distribution px from the data set x. So how to learn this prior distribution px? Remember that x is a data with huge dimension, more than 10,000 dimensions. This will be very challenging for our conditional model-based approach. For traditional channel modeling, there's no channel modeling attempt or method tries to give the channel modeling for the channel distribution for the channel. Let's say for the channel game, for the 1,000 or 10,000 locations, it is very difficult. But this is possible for generative AI approach because this is what exactly done for image processing. So let's say why we need to learn the prior distribution of px. Let's say this is the knowledge or the belief of the PDF for the x. Let's say if we believe that the px has a Gaussian distribution with a large variance, and then in this case there's a large uncertainty. But if the ground truth of x is very small, the variance is very small, but we did not learn this prior distribution, then actually we actually lose very much information. So this basically means that let's say if the ground truth distribution of x is very deterministic. Let's say it's a data function with 0 variance. It basically means that even there's no observation y, we can always predict s quite accurately because it is not a variable. It is not a random variable. It's a deterministic variable. It's a deterministic number. So in this case, it means that if we know the prior distribution of x, it will help to solve the inverse problem very effectively. But again, the key challenge is that for image x, which has a high dimension, let's say h by w by j prime, the dimension can be easily over 1,000 or even 10,000. Directly learn the prior distribution px is very difficult. What is usually done is that we use a generative AI, try to learn a distribution p theta x, try to approximate the prior distribution px. This is a joint distribution of all the possible locations, let's say the h by w locations of the channel knowledge. And most generative model cannot represent the PDF, but what we can do is that we can learn a neural network actually generate samples that will approximate the ground truth data distribution. So let's say we start from some simple distribution, x0, following from the simple Gaussian distribution with mean 0 and the variance I, the covariance matrix I. This is a very simple distribution. It's totally noise, random noise. After certain generative model, we can generate data samples x that follow certain distribution p theta x, depends on the theta, the parameter theta. And we want to approximate this p theta x so that it actually has the smallest distance with our ground truth distribution p data or px. But the key point is that we do not know px. We only have the data, the sample, the data set that follow the distribution px or p data. So this is actually the very challenging generative AI problem that try to generate data samples x based on some very simple distribution or Gaussian noise, so that the new data sample x new will follow the distribution of our ground truth data sample. Right? For example, if we have the image, the data set of images of dog, and after generative AI to generate a new image, the new data, the new image should look like a dog. So this is also true if the data set is our CKM ImageNet data set. This is a key point. Of course, there are different methods for generative AI. The key difference for generative AI and the convolutional discriminative AI is that, again, if we have the promote Y with the model, we can generate some output X. And the discriminative AI is that, let's say if we give you an image X, you want to tell whether it's a dog or a cat. So you can treat it as the reverse process. But the key point is that for generative AI, depends on your promote Y, the output can be many possible outcomes. So generative AI models actually have many different techniques. We may have the so-called variational autoencoder, or VAE, where we have an input data set X. We try to learn the mean and the variance mu and sigma of a Gaussian random variable. Remember that when we do the generative process, we will start the Gaussian random process. Let's say from this Gaussian random process, we can generate an image or data that looks like the ground truth data. We may also have the very famous GAN, or generative adversarial network, where we have a generator and we have a discriminator. The discriminator and the generator will play a game theory so that we can generate new data that looks like very similar to the training set. And of course, we have the very famous diffusion model. The key point is that we have a clean data set, and we want to reconstruct, we want to generate a new data set from the pure noise that looks like the data set. Then the first step is that we add noise to the data set so that eventually we will end up with a complete noise. And this is the forward process. It's very simple. We just add noise so that gradually we only end up with noise. But the key point is that is it possible, how it is possible to remove the noise during the reverse process, so that later on we can start from the pure noise or pure Gaussian process, Gaussian random variable, so that we can do the denoising, then the eventual output will be something looking like a cat. So this is a key point for the diffusion process. Now, our diffusion process was very, very famous, very, very successful. Most of the generative AI have used the diffusion process. It was the state of the art maybe 2 years ago or 1 year ago, but now we have the so-called flow matching, which is more efficient than diffusion. But due to the time limitation, we're not going to give the details for this kind of generative AI methods. What I'm going to show is that how we make use of the generative AI to solve the inverse problem. Let's say we consider this linear inverse problem. It can model the impending super resolution we mentioned just now. Again, we start from the data set that includes our clean CKM. Then the first step is the forward diffusion process, so that we add noise. And then the reverse process is that we train a neural network so that the input is a noisy CKM, the output is a cleaned CKM. And because we know for every step, we know how much noise we have added, so that we can train a neural network, let's say using a UNet to predict the noise we have added, so that eventually and hopefully we can recover the CKM, the clean CKM. But for this kind of process, remember that we have only make use of the data set X. How about the observation Y? For this pure diffusion process, we haven't made use of the observation Y. So maybe the CKM we have generated is just a random CKM. It does not correspond to any environment. In order to make use of the observation Y, we also need to train a neural network, so-called a conditional diffusion model network. So the input is still the data set X0, and we train a neural network, let's say a UNet. But in this case, Y, or our observation Y, will be also our input to the neural network. So that the denoising process will know how to denoise so that the output will be consistent with our observation Y. Then this is a so-called conditional diffusion CKM construction, so that the constructed CKM X will also follow, not just follow the distribution of the CKM distribution, but also consistent with our observation Y. So we have one paper that gives the details for this kind of process. So this is how it looks like. We have compared the diffusion-based super resolution based on the CKM ImageNet dataset and also some other dataset. So the first column is a ground truth, CKM. The second column is the observation, is a degraded observation. The third column is the reconstructed CKM based on the proposed diffusion method. And we have also another of some other benchmark schemes. We can find that our proposed CKM is very clear. There's no blurry or no ambiguity. And it actually significantly outperforms the conventional benchmark method. For example, for this kind of interpolation-based method, bilinear or bicubic method, it is a blurred method. We have blurring because, as we mentioned, we have the so-called regression to the mean problem. And we also compare the different KPIs, let's say the RMSE or normalized MSE for the diffusion-based CKM construction. We can find that for both the CKM ImageNet dataset and also other dataset, our proposed diffusion actually achieve much better performance. But for this kind of diffusion-based CKM construction, it also has a very big limitation, which is the slow inference speed. We saw just now for CKM, for diffusion-based CKM construction, we need to use thousands iterative steps to do the denoising process. this actually will be very slow. Actually, this is not just for CKM construction. For diffusion-based image processing, the inference speed is a big issue. But fortunately, recently, the so-called flow matching can greatly speed up the process. So what is the flow matching? Flow matching actually can be also used to solve the same problem, the inverse problem. So the basic idea is like this. We have a data set X, and we can do some observation process to obtain Y based on this data set. This will give us the condition. The condition will include both both the observation Y and also some other environmental information. So this is from the data set. Remember that for generation process, we need to start from random process like a Gaussian random process or Gaussian random variable. So this is a very simple distribution. X0 is a Gaussian random process or Gaussian random variable. So as an input to the a network, so C and also the sampling from the Gaussian random variable will be the input to our random the neural network. The output will be the so-called velocity vector. So what does this mean by velocity vector? The velocity vector will guide our process so that we can output the high resolution image X based on the degraded observation. So remember that this is exactly what we want to do. We want to, based on the observation Y, to infer X, but in this case, we use the so-called flow matching process. So the details are not given here. The basic idea is like this. We can sample a random vector X0 from a Gaussian random variable. And we may also sample a clean image from our data. Then if we want to guide our process from X0 to X1, which is our data, then the straight line, the velocity, the difference of these two vectors will be just the velocity or the direction where we need to do the flow process. So in this case, if for every input X0 and X1, we know the velocity, so essentially that we can just solve the ODE, ordinary differential equation, to find the ground truth X. And it is very different from the diffusion, because for diffusion, it actually solves the so-called stochastic differential equation, where the speed is a big issue. So we're not going to give the details because of the time limitation, but here we try to show some results for the flow matching-based CKM construction. Here we have the observation of the CKM, which is a low-resolution image, and we have the benchmark based on the interpolation KNN by linear and by cubic. And also we have the DDPM. DDPM is a diffusion-based method, and we have the flow matching. The last column is the ground truth or the high resolution CKM. We can find that our proposed flow matching method have very comparable result as the DDPM or diffusion-based method, but we can see here the inference time is much, much shorter than the DDPM or diffusion-based method. It is always almost 1 order of magnitude or even 2 order of magnitude of the time saving for the speed. So in this case, the flow matching-based CKM construction is quite promising. So far we discussed how to use the supervised learning, also diffusion and flow matching-based method to solve this kind of inverse problem. The basic idea is that we try to infer X based on the observation Y, and we can learn something from the data set. Let's say learn the distribution of the data of X. So basically, if we just use the so-called MAP-based estimation, this is a well-known estimation. So given the observation Y, what is the most likely probability that this X is given by Y? So this is the so-called MAP, maximum posterior estimation. This is a well-known and quite standard. So based on the Bayes rule, we can decompose this posterior distribution as a prior distribution and the likelihood function. Py given an x is the likelihood function, and px is the prior distribution. The key point is that this prior distribution need to be learned from the data set. But the beauty is that remember that this prior distribution does not depend on y, and it is independent of this so-called forward observation process A. So this basically means that if we have collected a large data set X without any observation Y, just the pure CKM from anywhere on the Earth, then we can do something to learn the prior distribution without knowing what to do next, without knowing the downstream task, without need to specify the Y or the forward observation A. So this actually gives us a very convenient framework to do the so-called generalizable prior distribution learning based on this diffusion posterior sampling. So the beauty is like this. Let's say the base station have collected a large number of channel knowledge, and we have processed this channel knowledge as image-like X. So we only have X. Let's say X contains each X contains 10,000 locations with their respective channel knowledge, and we can aggregate all the channel knowledge X into a cloud, and based on this unlabeled data set X, we can learn the prior distribution Px, and this prior distribution Px should be shared by all the CKM on the Earth, no matter it is in which city, right? So in this case, now we can share this Px to all the downstream tasks, whether it is a quantization recovery, imprinting, or it is a super resolution. They share the common Px. So this actually will give us a very, very convenient so-called foundation model for multitask CKM construction, because the prior distribution we learned can support multiple downstream tasks. So we call this a CKM foundation. So here we show the result we have obtained based on this foundation model-based multitask CKM construction. So let's say this is our observation, and we have the ground truth for this proposed method, and we also have some benchmark. Benchmark is the end-to-end training for one specific task. We train one neural network. So we can find that the proposed foundation model-based multitask CKM construction can achieve comparable or even better performance than the baseline, but it only requires one common AI foundation model. This is quite promising because we do not want to train one neural network for each task that is not efficient. So this will actually very promising and very efficient for CKM construction based on the foundation model. Okay, so so far we have discussed how we can make use of the generative AI for CKM construction. So last time, we mentioned that if you want to develop a so-called non-transferable CKM construction method, it is not that difficult. But if you want to develop the transferable CKM construction, it is more challenging. But fortunately, if we view the CKM construction as an image processing, we can actually eliminate the dependence on the absolute location. And it is very efficient, very effective to model this problem as an inverse problem. It can be linear, it can be non-linear, but we have a unified mathematical framework for CKM reconstruction, and it is transferable. And it can make use of not just the observation Y, but also the data set we have collected all over the world. And because the inverse problem is ear post, the key is to learn the prior data distribution Px. But because of this X is a huge dimension, it is very difficult to leverage the conventional channel modeling for this purpose. So we need to make use of the generative AI approach, and the diffusion and flow matching are quite promising methods. And we can also make use of the foundation model to support multiple downstream tasks. But there are still many open problems. Remember that just now we discussed many different ways to specify the environment. It can be the radar, it can be the LiDAR, it can be the cloud point, it can be the language description. But so far, we only discussed the environment is specified by some sparse observations. How to make use of the multi-model information to describe the environment and develop efficient CKM construction algorithms is still open, and we are going to solve this kind of problems. Okay, so here again are some major references from our group. We have tutorial and magazine papers, including the first paper in 2021 that proposed this concept. And also in 2024, we have the tutorial paper. And we have publicized the data set called the CKM-enabled, both in the GitHub and in Hugging Face. And we have some CKM construction methods and some CKM utilization for sensing localization. And also we have developed some very preliminary prototypes for CKM. Okay, that's all for today. And I'm very happy to take any questions. Thank you.
Okay, thank you very much for Professor Zeng Yong for the very comprehensive talk on CKM construction by using different types of generative AI methods. So the talk is quite interesting and inspiring. And we got a number of questions. So the first question is as follows. So about the generative AI for CKM construction, are these generative methods such as diffusion models or GANs primarily used for imprinting missing data in sparse measurement areas, or are they designed to synthesize the entire virtual channel maps directly from the 3D geometric environment? I think you may clarify. What is the exact problem?
Thanks for this question. Yeah, indeed. In principle, this kind of generative AI methods, let's say the diffusion, flow matching, GAN, can be used to construct the CKM based on the multi-model input. Let's say not just for imprinting super resolution, it can be based on the observation, as we mentioned. Let's say the vision, even the language, even the radar sensing. Yeah, they are possible. And in principle, it is possible. But the key point is that so far, we do not have a sufficient data set to support such kind of generation. Because basically, we need to do some mapping for the, let's say, the point cloud and the channel knowledge, and also some other multi-model input to support such generation. Unfortunately, to my best knowledge, I do not think we have the readily used data set for this kind of construction. But for the imprinting super resolution and denoising, our proposed or developed so-called CKM-enabled can be directly used to support such kind of reconstruction based on the generative AI, diffusion or flow matching. Yeah, I think the next promising research direction is to develop such data set that can be directly used to support a multi-model input-based CKM construction.
Okay, thanks. The next one is, I think, is related to the inverse problem you just mentioned in this slide. So in the formula y equal to a of x plus n, the noise n can stem from quantization errors or localization offsets. So during the super resolution reconstruction, how do we distinguish between artifacts caused by noise and the true fast fading channel variations?
Yeah, that's really a very good question. That really depends on the so-called channel knowledge that we want to learn. Remember that last time we mentioned that we have different approach to model the channel knowledge. So the channel knowledge is that, let's say, if we want to learn the direct channel gain, including both the path loss, small-scale fading, and shadowing, that will be very challenging because as the audience mentioned, for every measurement, we may have the small-scale fading. Then if we directly learn this small-scale fading, that will be very, very difficult. So that's why last time we mentioned that a more promising approach is that we try to learn the conditional PDF, conditional probability distribution for this channel knowledge. So it can incorporate or can deal with any small-scale fading or any variant or any dynamic environment, so that what we have learned is more stable knowledge about the channel. So let's say we can learn the mean or the variance of the channel knowledge at that particular location if we assume the Gaussian distribution, or it is other distribution. We can also learn the mean or the variance. So in this case, the key is to do the data pre-processing. So far, we only mentioned the data pre-processing to convert the raw data into image. But actually, last time, we have mentioned how to do the data pre-processing to process the, let's say, the random data that includes both the dynamic environment, the small-scale fading, the shadowing into some more stable channel knowledge that is easy for us to learn. And I think that is also key. So let's say if we learn the mean and the variance of the channel gain, then this is much more stable, and then the small-scale fading can somehow be the effect of the small-scale fading can somehow be eliminated during the pre-processing.
Yes, you mentioned that you're going to use a PDF for each the channel at each point, right? But in the generative AI method, so how can we process the PDF? So do you mean that we can view each pixel of the image as maybe the mean value, right?
Yeah,
and you can
exactly.
learn the PDF separately. Is that
Yeah, exactly. So it depends on at each pixel location, which you want to learn. Right. So for example, for the natural image, for each pixel, it is just the pixel value for the RGB from 0 to 255. But for our CKM as a conditional PDF, it really depends on how we model the PDF. A very simple way is to model it as a mean, as a Gaussian. So we only need to learn the mean and the variance of each pixel. But of course, this is a limitation because maybe the ground truth is not Gaussian, and then it is more challenging. But if we model it as a Gaussian, then we just predict the mean and the variance of this Gaussian. For each location, the mean and the variance will be different. Then for the generative AI, the CKM will just give the mean and the variance of this location, and based on this location, we just give the Gaussian distribution, the conditional Gaussian distribution. It can be extended to other distributions or more complicated distributions. Yeah.
So I got another question that is quite interesting, and yeah, I also have the same similar question. So actually, the layout and the architecture for each location, right, or for each area are different in practice. And so the question is, so if you build a data set, right, how can you ensure that the data set has a good generalizability?
Yeah, that is really, yes, it is indeed a very important question. Actually, this is very similar to the computer vision for the image generation or image restoration. For computer vision, they also have similar issues. Let's say different images may have different size, different resolutions, and so in computer vision data set, they have quite standard data set. Let's say this very famous the ImageNet data set. So that's why we use the similar terminology. We call it CKM-enabled, which was motivated by the data set from the computer community. So we have the similar issue here. That's why it is quite important to pre-process the data set or the data to somehow the standard manner. Let's say here in our so-called CKM ImageNet data set, we have processed the data into the standard 128 by 128 pixels. For each pixel, the adjacent pixels are separated by 2 meters. And of course, we have another standard. I think we also have the 64 by 64 image, because 128 and 128, the number of pixels is too large, and it requires a huge computation resources. So that's why we also have I think we have a 64 by 64 pixels. So that's why we need to do some standard processing for the data, for the raw data. And I think this was not considered in the traditional data set for, let's say, for the traditional channel modeling. For the traditional channel modeling, we do not have this kind of issue. But if we want to make use of the AI method or the computer vision technology for this kind of CKM reconstruction, this is quite important. And I think it will be very, very promising if we have this kind of data set. And of course, we can also develop more robust architectures and AI learning methods so that we can deal with different, let's say, the heterogeneous sizes or resolutions of the image. And I think that is doable. And the computer vision community have the similar issue. We can do some techniques to deal with the different data sources. But the key point is that we need to have some standard, and this standard is where acceptable for different communities, and it is a balance between the learning capability and the computation resources. And there is actually a lot to do for this kind of process. Yeah, that's my understanding.
Thanks. Another follow-up question is also related to the data set. So the audience asks, how do you obtain the data set? Do you get it through the actual measurement or simulation? And another related one is when you get the data set, right? Because you mentioned that you can use a PDF to represent the CKM, but when you get a data set, how do you know the ground truth of the statistic CKM?
Yeah, thank you. Yeah, it's really also a very important and a very good question. Actually, I think for this course, we will have a separate lecture for the data set. So today, we didn't give too much details about the data set. But for the question, for the data set we mentioned here, we use a ray tracing technique to obtain the data set. The basic idea is that the data set should reflect the actual wireless propagation mechanism. So let's say in this case, we need to really generate the data set based on some physical environment. So given the physical environment, we specify the environment, we specify the materials of the environment. So we use some standard ray tracing techniques. Let's say some commercial ray tracing software, let's say the Wireless Insight or the Siona or MATLAB also has the ray tracing program. So based on this, we can obtain the angle of arrival, angle of departure, and the delay, and so on and so forth. So the key point is that if the data set should be useful, it needs to reflect the actual propagation environment. So that means that our original or our traditional, let's say the model-based data generation based on the Bayesian relay feeding channel model cannot be used to generate this data, because no matter how you generate, how many data you generate, then the basic principle is just relay or Bayesian feeding, then that is not useful. So here, I think the ray tracing data is very important and is very useful as compared to the measurement-based data. It is more efficient, more effective, and we can generate many data. And it can also reflect the actual propagation environment and also the wireless propagation mechanism. So that's why we chose to use the ray tracing to generate the data. But Yeah, I think the point that if we generate the data, how to, let's say, for the conditional PDF, or how to generate data that reflect the dynamics. I think this is also quite important question to further develop, because for this CKM ImageNet data set, we haven't considered the dynamic environment. But I think the principle is not very difficult. The basic idea is that we have the buildings, we have the static environment, and then we can introduce some dynamics. And then for any scenario, we can use ray tracing to get the channel knowledge or the channel gain, channel angle of arrival, delay, and so on and so forth. So this is just one piece of the data that we can record. And then next time we can introduce another dynamic, and then we can get another piece of data. So by repeating the process, we can actually include the dynamics into our data set. And then based on what we discussed last time, we can do some pre-process to convert such a kind of data to the conditional PDF. And then we can just learn the major parameters of the conditional PDF based on what we discussed today. But so far, we haven't done this yet, and we're still working on it because of the long process to generate the data and the required computation resource to introduce the dynamics. And another question is that how do we know whether the generated data will match with the ground truth? Frankly, we do not know, actually. We do not know the ground truth, because that really depends on how you define the ground truth. If you define the ground truth as the measurement-based data, that will be very, very challenging, because even the measurement itself has certain non-ideality, because it has certain noise, a certain ambiguity, and so on and so forth, right? But if we want to if we define the ground truth as the ray tracing output, then that really depends on the quality or the reliability of the commercial software, let's say the Wireless Insight, the Siona, and so on and so forth. So the key point is that we do not try to learn the CKM with the ground truth. We try to learn the mechanism. We try to learn the propagation mechanism, let's say, given the environment. So what is the mechanism for this kind of data and the environment, the mapping and the propagation mechanism? And then next time, let's say if we have the measurement data, then if you give me my measurement data and this data is very reliable, and then the same principle can be used to apply to the new data set. And I think it is not too difficult to generalize. And of course, most of the case, maybe we have the simulation generated data and the measurement data, and then we need to do something more in order to have more robust and more efficient CKM generation. And I think this is also a very promising research direction to go deeper. Yeah, that's my understanding.
Okay, so the that's the question. So I just wonder, right? Because for this, you use some generative AI method, which is basically used for images, right? And you model them for the CKM generation. So I just wonder, because in the real environment, especially a lot of these people are interested in the low altitude networks. So we're going to have a 3D network, right? So how to extend the image-based processing to the case with 3D scenarios? And another related question is that, so when we use a 2D image, this basically means, if I understand correctly, right, this means that the transmitter or receiver location, so one side location will be fixed. So how can we extend to the case when both transmitter and receiver may have different locations? In that case, you're going to have a 4D or 6D, right, channel knowledge map. Yeah.
Yeah, these are really, really good questions. The first question, how to extend the diffusion or generative AI to 3D? Yeah, this is very important, because the conventional, the traditional diffusion or generative AI are mainly based on 2D. And here we have, I'm not sure whether we can see this reference, the reference 5. We have tried one we have made one effort to this so-called 3D CKM construction for the low altitude communication and sensing. This is exactly what we are trying to achieve, but because of time limitation, we didn't give the details. Here we use a very simple approach. Is that for 3D for the low altitude environment, one possibility is that we just partition the 3D environment into slices, into 2D slices with different altitude, so that we can learn the joint distribution within one slice, which is the traditional 2D image processing. And we can also learn the joint distribution across different slices, across the different altitudes. So in this case, we have the additional dimension to explore for this kind of 3D CKM diffusion. But as you mentioned, it is more challenging, and it requires much more resources, and there's still much to do. And I think your next question is also quite related to this one, and it is even more challenging because if both the transmitter and the receivers are mobile, we have the so-called 4D or even 6D CKM construction. But I think the basic idea, basic principle is still applies. But frankly, I do not have too many ideas for this kind of scenario. I think Professor Xu yourself has some very interesting work based on so-called Gaussian splitting, right? I think this will be a very promising direction, because for the 3D or higher dimensional data reconstruction, we have the Gaussian splitting technique. Maybe that will be very promising. And I think again, there's still much work to do. Yeah.
Yeah. Okay. Thanks. I will talk about that in the next lecture.
Okay. Yeah.
So, okay. So due to time limitation, so maybe we should stop here, but we still have some other questions in the chat box. So sorry that I cannot ask all of them here. So I think all the questions will be posted at the TaskPark website. And so Yong, you are invited to maybe check these questions, and you can answer them offline. Okay. So okay. So thanks all. So thanks Yong for the very nice talk and very interesting and insightful answering. And thanks all for all the audience for your attendance. Okay. Thank you all, and maybe
thank you, Jie. Thank you all. Bye bye.
Thanks. Bye bye.